Okay, we're recording. So any questions on any of this? And we're going to go through it all anyway, but if there's any specific questions at the beginning, we can address that. Okay, then what I'll do is we'll start going through these presentations, and I just want to talk through some stuff on it. It'll be helpful for your guys' exam. And then we'll reevaluate if you have any more questions on landslides, and then we'll switch over to floods. Now, if you guys have a question at any point during this, just just say, chime in. We're more than happy to stop, answer as many questions as we need, okay? So the first thing, let's see, I want to start here. I kind of want to just go over with landslides, just with this exam. The way that this exam asks its questions about any of this material, about landslides, anything like that, is a lot of times just, it's not so much like what's the angle of repose, things like that, but it's going to be a little more oriented to things like, you know, talking about, I'm trying to find a good example in here. Maybe like some of your case studies, what kind of slides that some of your case studies were, things like that. And since those can be hard to study from, they're going to get posted tonight. One more thing, just some documents I came across that will have a bunch of information on every single case study that will answer any question you need for the test, so you guys can look through. But to start off with, I'm just going to kind of move through some slides quickly and some a little slower. Biggest thing here on this slide with landslides is there's a thing called angle of repose. It's what they're talking about right here. And basically it is that there's an angle after which if you exceed this angle, stuff will just start to naturally slide down. Gravity is going to pull it down. So typically 35 degrees and up. So just let this figure here, fine sand, 35 degrees, coarse sand, 40, angular pebbles, 45. 35 is kind of the rule of thumb, 32, 35. Anything above 32, 35 degrees is at risk for failure. So if you remember, what are some of the things that can cause failure or that can cause mass wasting? One of them is angle of repose, exceeding angle of repose. What are some of the other things? I got a chat here. Let me open it up. Sorry. Yeah, water. So Karen, what do you mean by water? I know it takes a second to type, so we can wait. That's right, loosening the sand. So as you saturate the ground, it can basically, your sand's compacted together. As you put water in, it can kind of float the grains apart, makes it a lot easier for you to have mass wasting or land, which is, just a landslide. So you can get your water, which will destabilize things by loosening the ground soils. What's something else that can cause mass wasting? Anybody? Yeah, cutting the slope off of a hill. So let's say you've got, a hill right here, and then you decide to cut off this bottom end. So rather than being like this, it's more like this, and you've got this big slope right up here. What'll happen is that it can destabilize the slope. There's not as much stuff supporting it up, and this will actually break off and slide down. So great, cutting off the base of the slope can really cause a problem with that. Yeah, great. Anything else that anyone else can think of? So there's a few here. There's another one. Earthquakes. So an earthquake can trigger a mass wasting event. This would be, it kind of makes sense. The shaking can cause steep slopes to collapse, can cause breaking along planes of weakness. This would be things like the layers of mud or clay that in the rocks that break really easy. Volcanoes can also do it. I don't know if you guys remember in Mount St. Helens, but there was a big landslide that associated with it as well. So the volcanic lava can melt snow at rapid rates, causing a bunch of rocks to come down. And if you guys remember, as it melts snow and glacial ice, and it comes down the mountain picking up debris, what's that called? You guys remember? One of the things we talked a lot about on the week of volcanoes. Yeah, it's a lahar. So a lahar is just a form of mass wasting, right? That's formed by a volcano. Okay, you got slope saturation, which Karen mentioned earlier. That's just where you get heavy snowfall, rainfall, uh, changes in groundwater, and basically it just makes it so it's easier for it to collapse. Flooding, which will associate with that, right, um, can cause destabilization of um, your slopes by saturating the ground, but also just because it can remove material that's supporting it, and just generally weakens it. Um, so yeah, it talks about this. You can also get things with like landslide dams. You guys remember reading through the case study of Thistle, Utah, right? There was the mud flow or debris flow that came down and it dammed the river, right? And it created that big lake. So you can get this isn't necessarily the damming of the river isn't the cause of the landslide, but it's a result of the landslide where it dammed the river to create a big lake and completely inundated the town of Thistle. So those are some things there. Landslides and earthquakes, common in mountain ranges, right? You can get the shaking. You've got the steep slopes. You can destabilize it. Don't want to spend too much time on this. It's not really going to ask you anything about the 1964 Great Alaska Earthquake. Landslides and volcanoes. So this is the Lahar right here, looking off of Mount St. Helens. On the other picture, you've got the Lahar off of Pinatubo. So big case studies that you guys read about. Um, so you can see they're very damaging and cause a lot of problems, right? This went right through a town, you guys can see. So very, very, very dangerous form of mass wasting. And if you guys remember, the lahar forms by the volcano melting the snow and ice. It doesn't have to be during an eruption either. It can just be as the ground's heating, because remember, as the magma rises, it'll heat the ground and it can cause the melting of the ground of the ice and the snow, and the eruption would do the same. And all that water is going to go rushing down the mountain, and it's going to pick up debris. So it's going to pick up rocks and trees. It's going to pick up, the top layer of soil and gravels and all that, and it's going to create this thing that's going to come rushing down the mountains and down the ravines at, up to 40, 50 miles an hour. Okay, so very, very dangerous. Then there's also some other things, some destabilization that we can do. Was mentioned a little bit earlier, right? We can remove the bottom end of the slope. So that's what they say here, undercutting the bottom of the slope. There's also loading the top of the slope. So you see this a lot in construction, actually, where companies and people will build homes up on top of ridges and slopes, and they can overload the slope, and you can get eventually a mass wasting event there. Not so much now. Zoning laws and things like that try to avoid that, but that's one way you can cause it. Can also be caused by change in drainage patterns. This can be from, any of these things. So broken water, sewer lines, draining of reservoirs, improper excavation or grading of slopes. Just things, anything that'll change the direction and movement of water down slopes can cause that. And then the last big one is removing of vegetation. Now, why would the removal of vegetation put a slope at greater risk for failure, for mass wasting? What do you guys think? Any thoughts? Okay, we got a chat here. That's right. The roots hold the soil in place. As a matter of fact, there's a lot of roots of like your grasses will go 6, 7 feet down, and they'll really help to stabilize your slope. It's kind of like a net that holds the ground and the dirt and the soil in place. So if you take all that off, kill those plants, and the roots wither and dry and die, all of a sudden, well, hey, there's not as much stability in that slope. It's the same principle as like when construction companies put all the rebar into the cement. That soil is held by the roots in a very similar fashion that acts like a rebar. Very good. Okay, we'll skip human activities. Other things that can make it more likely. So weak materials. If you guys remember in the reading, when you guys read through this, things like talus, shale, silt, sand, gravel, those things can cause that a failure. So if you just have a really weak material that's really easy to break or really slides really easy, that can make it a lot more easier prone to have a landslide. Also on top of that, steep slopes, which makes sense, right? You know, if you've got a cliff or a really steep slope, it makes sense that that is an area that is likely going to have a landslide with a lack of vegetation as well. So keep moving. Climate, arid, semi-arid regions that can have a brief but intense wet season, followed by, again, low precipitation can be at risk for these landslides. So again, just think of it this way. The soil is not getting any water for 8 months out of the year, then all of a sudden for 3 months it gets a lot of water. All of a sudden that soil is saturated with liquid, and it's really easy, it kind of, right, destabilizes it. Again, the sand grains float apart, and it's really easy to move down. Okay, tilted layers are the same. You tilt things, you've got a layer here that it can break along, and the gravity can just naturally pull it down. Typically clay layers are those areas that'll break along. So we'll show this. This is a good example. Here you've got a layer of clay, okay, and it's got a slope there. What happens sometimes is as gravity's pulling this down, it will actually break along this layer right here where you can see, and it'll slump down. This is a slump right here that you can see. If you guys remember, that's this type of landslide. So this is a slump that's slumping along this basal clay layer that's really weak, really easy to break. Okay? Okay. Next one. This is a really good one because there's a test question that comes from this. So take note. Now you may not get this test question because a lot of the tests, it kind of like randomly chooses from a pool. But there's like a really good chance you'll see a question like this saying, where are some good locations, where are some likely locations for landslides to occur in the United States? And the simple answer is wherever you have topography, wherever you have, you know, hills or mountains, it makes it really likely that that's going to be a region prone to a landslide. And if you look at this map that backs it up, right here you have the Appalachian Mountains, you've got some hilly regions in here, and then right here you've got the Rockies and all the Cascades, mountains over along here and everything, all the hills and beautiful stuff along California, Washington, Oregon. These are all regions that are prone to landslide, okay? And that's where you've got topography. It's where you've got some of these places a dry climate that will get a lot of moisture during certain times of the year. So these are really prone. These are the areas that are prone to it. So looking here again, you can see the Appalachian Mountains, the Rocky Mountains, Pacific Coast Range, parts of Alaska and Hawaii that have severe landslide problems. They say any areas composed of very weak or fractured materials resting on a steep slope can and will likely experience landslides. So basically mountains, where you have mountains, that's where you're going to have it. Okay? Any questions on that? Make sense to everybody? Okay. So this is just talking about it. We're going to keep past here. So this right here is a landslide in El Salvador. You can see there's a big slope here. The areas that are prone, typically steep slopes. Another thing that you'll see often is there was already a landslide that happened there. For example, if you remember, the case study briefly mentioned this, but the Thistle, Utah landslide was a reactivated landslide. So that means there was a landslide there a long time ago before people had ever come. And then we had another one of those really, really wet years, and then the Thistle slide happened again, right near the same spot. So if you see that, that's a good indicator that that's likely going to be where a landslide happens. Okay? So just for life, areas that would be a good, safe place to live where you wouldn't have to worry about it would be on hard, unfractured bedrock. So that's when you're living on, big, a relatively flat place, low angles that has really hard, the rock underneath isn't like sandstones or clays or muds. But if you dig a little ways, you start to see granite and things like that. Okay, that's kind of what you want to live on. Okay, and we are going to hop over to another presentation. Any question on these slides we just looked at? Okay. Now we're going to talk about the types of landslides. Okay, this is important to know. You want to know the different types. And so you've got this figure here. I'd recommend coming back, spending a few minutes just looking at this figure, and then this figure. This figure right here that shows the types of landslides is probably one of the single most important figures for landslides. So this one's great because this one shows you the different types of landslides and what they actually will look like. So you've got a rotational landslide or a slump. You heard me call it a slump on that one where we were looking at the clay layer, right? And that's where you've got a landslide like this, and then rather than sliding straight down, it kind of actually slumps as a kind of a curving motion. You can see that here looking at this. It curves like there's a kind of that rotational element to it. It'll kind of look like stair steps on it. Then there's what's called the translational slide. That's simply, and if you look at my hands, I know you guys can see me off to the side, right? I hope so. Okay, I've got a couple of chats to see. Okay, perfect. Sorry guys, I talk a lot with my hands. It's a geologist thing. A translational slide is just where it's sliding along a plane, right? It just broke along a plane. Okay. And then, all right, we got a chat here. Let's see. Okay. So then you also have a block slide, which is similar. It's sliding along a plane, but it's more like a big block, like a big chunk of rock comes down. Whereas a translational slide, it's more just like a whole bunch of mud and other stuff kind of all coming down at once. One's blockier and one's a little more sorry, there's a chat, guys. One's blockier and one's a little more homogeneous, if that's the right word. I'm using geology words there. Some of you are probably like, what in the world is he saying? Sorry. It's more like a bunch of mud and a bunch of other materials, where a block slide is more like you're looking at a piece of clay, like a side of a road, and you see a whole block of rock, one just solid chunk of rock that slid down. I'll show you here. Okay, translational landslide. Okay, see, this is more of a translational. It's just saying it's along a plane, right? It's a bunch of soils and muds and stuff like that. And then block landslide. Not sure. Can find this diagram is good enough. It's like you can see up here, it's a whole moving block. One solid block is translated down the whole thing. Okay, does that make sense to everybody? The difference between the two? I'm not hearing any questions, so we'll keep moving with that. You've got a rock fall, which is pretty intuitive, right? That's just where the rocks fall down. And a rock slide, there's a bit of a rotational element to it. It's not a big block of rock like this moving on at once. It's a whole bunch of rocks coming down. They can slump a little bit and they'll just come down. You've got a debris flow, which we've talked about, right? The debris flow is where it picks up soils and dirt and trees and all that, oftentimes from meltwater, from the snow, from heavy rains, things like that. Okay, and you've got a debris avalanche, which is actually a whole section of ground is just fails, kind of, right? It slumps a little bit, and it all comes down like a giant avalanche. It's a lot like a mud flow, earth flow. So a debris flow or a mud flow or earth flow, excuse me, is very similar to a debris avalanche. Okay, and then you don't really need to differentiate between those two. Now, creep is where it just slowly translates down the side of the mountain over a long period of time. You can see this on hillsides, right? Well, there's a picture later on we'll look at really briefly. Got those trees where they're kind of curved at the bottom. Almost looks like the tree started growing out and then the ground shifted and it straightened out. So it looks like they're at an angle at the base. That's just showing that it's slowly sliding down the mountain. Sometimes a few centimeters a year. Sometimes it's, a couple of or maybe a couple of inches a day, or not a day, but a week. So, okay. Then there's lateral spread, which I'm not going to explain. There's not going to be anything on the exam about lateral spread that I remember. So, just a sec, guys. I got to plug my computer in. Hey, Sheree, can I get you to plug that into the outlet for me? Will you plug that into the outlet for me? Thanks. Okay. Here, and this is a good caveat too, right here that they have. Creep refers to extremely slow movement, whereas an avalanche refers to very fast, rapid movement. Okay. What makes this slide so good, they've got the different types. They've got movement type, and then just the type of material that falls in it. So a rock fall, a debris fall, an earth fall, a rock slide, debris slide, earth slide, just different things. The biggest thing that I actually want you guys to take away from this isn't so much over here where it's talking about the types of materials, but is these first two columns, the type of movement and the rate of movement, right? So a fall is a very, very fast movement, whereas a flow is very, very slow. So just know that a fall is faster than a slide, which is faster than a spread, which is faster than a flow. Okay? All right, so this is just going to briefly explain a little bit of them. I would recommend coming back through, watching the videos of these. I'm sure you've already done it. So rock fall, you've got the rocks falling down the side of a cliff, very fast movement. Rocks are what's going on there is the rocks become loosened through erosion. You can get water flowing into the cracks along the rocks, then it freezes overnight, and water expands when it freezes, so that expansion can actually make those cracks worse and weaken the rocks so that they fall. Earthquakes, freeze thaw wedging, frost thaw, which is what I was just talking about, intense rains, things like that can cause this type, okay? Here's some examples of rock fall. Here's a picture of one as it's happening. Big cloud of dust as all the rocks come tumbling down the side of the mountain. Right here's an image showing this where some of these came falling down, went in people's backyard, right there into their house, right? Very dangerous. That's why you don't live near cliffs. This is one in St. George. This is a boulder that came down in Provo, Utah, not far from where I used to live. Went into someone's house. So very, very dangerous. Then you've got rock slides, okay? And this is key right here is this first sentence. A landslide involving bedrock in which the rock that remains largely intact, not completely intact, and it's not like these rock falls where it's completely falling apart, for a large portion, for at least a portion of the movement of the slide. So they're sliding down. They can be small, they can be thin to very big and thick in their scale. So they could be just 3 or 4 feet thick, or they could be 10, 15, 20 feet, 30, 40, 50 feet, not 50 feet so much, but 15, 20 feet thick. Let's see. What else do I want to hit on this slide? They slide along a surface typically. It can be curved. It can even be a little planar sometimes. They're not going to really differentiate in here Up here on this slide, you've got a translational slide and a block slide. They're just, for the purposes of this and the exam, what they're going to do is they're going to lump translational slides, block slides, and rock slides all as one when it's rocks. Okay, you can have a translational element, you can have a slump or a rotational element to it. Does that make sense to everybody? So it can be along a flat plane or it can have a bit of curvature. It's more a rock slide. When we say rock slide, it's denoting the type of material and the speed at which it's moving. And that's kind of why this was right here is really important. A slide type of movement is saying that it's slower than a topple or a fall, faster than a spread or a flow, okay? So back down to here where we are. Here's a good example of a rock slide. This is a translational one. You can see there's a big flat surface right here. It just literally slid down that surface. It was probably weak, had a little layer of clay right through there. The water saturated or in there, maybe froze overnight, and when it thawed again, it had wedged a big enough gap in there that the slope just broke and came down over the road. Okay? So these are typically on slope gradients. They're 35 to up to 75 degrees steep, so they're pretty steep. So yeah, we'll keep going from there. A slump, this is just where we have the rotational element. It's still a slide if you look down here, but it's got that rotation to it, kind of that scoop. You can see it really good right here. And it just kind of, this bottom plane is what it slid along. So it slid down here, popped up, and then flowed down this way. These are kind of characteristic, easy to recognize by kind of this stair step look to them right here. So you can see here's like, almost looks like you could walk up these as steps. And they kind of have like a bowl shape as well. That's kind of how you see a slump. Yeah, curved scarps, terraces. They're a little more fluid, kind of similar to an earth flow or mud flow near the base, the foot. So this area where it kind of pops out, a little more fluid like a mud flow. Okay. Here's a debris flow, and this is what they say a soil flow. It's a good way to think of it is it's just all the debris that's picked up by water rushing down the valleys. So it's going to be the topsoil, rocks, cobbles, trees, all sorts of stuff like that coming down the side of the mountain. Okay. So here's some images of debris flows, and you can see just how destructive these debris flows can be. I mean, you know, it completely collapsed everything on, or half of the building on the left, or excuse me, on the right. And on the left, you can see it just completely came through and caked all of this town in mud. Because what happens is when it stops flowing, it's not like water where it recedes. It'll shrink down a little bit, but it's going to leave, you know, tons and tons and tons of rocks and debris and all of that just laying around, caking these towns, sometimes completely burying homes. So to give you an idea, looking at this rock right here, this rock, this boulder, excuse me, which is probably 18 feet, is a rough guesstimate in tall, 18 feet tall, between 12 and 18 feet tall, was transported in one of these debris flows. So this gives you an idea of just how powerful debris flows can be. As a matter of fact, I want to show you guys a quick video. And I'm sure you guys have watched some of these. We'll just look at this one. So you can see this flow. It's very fluid coming down. This isn't my favorite one. There's a really, really good one. I wish I knew where it was. But you can, You know what? I'm gonna see if I can find a better one. We'll look at this one right here. Look at all those boulders and rocks moving at the head here of this flow. That gives you an idea of the power. These rocks are probably, you know, a couple of tons in weight. That this thing is just pushing down the mountain at 30, 20, 30 miles an hour. Okay. So when these come into towns, they have immense destructive force. Okay. And so these are slower. Remember, these are slower than slides and falls. Now, what the thing with these are typically these can be a little more pervasive. And if we go forward a little bit, where is it? Well, not worth it trying to find, but um, let's see if it shows the town. No, it's not going to show too much. Anyway, you know, these will push cars. Once they get into the city, they'll start pushing cars and everything just down the side of the road. So very, very destructive. Okay. This is a great picture. I think this is a really, really cool picture because it shows multiple mass wasting events. So you've got your mountain here, very, very steep gradient. You've got a debris chute, which this is just where the flows will come down. And you see these fan-shaped items here. These are all from where mass wasting events, debris flows, rock falls and slides and all that have all accumulated down into these big fans. So this is just showing that these slopes oftentimes are at extremely high risks, oftentimes multiple times a year, that the debris is going to come down. Okay. All right. Mud flows. Okay. So a debris flow has a lot of debris. So it has big boulders, you know, bigger than a house, and it has little things of mud. A mud flow is mostly just mud, fine-grained soils of silts and clays, and it's just this big, incohesive mass of mud coming down. I hope that makes sense what I was explaining. Well, I'll show you a picture. That looks what a mud flow looks like. You can see you don't have all the big rocks and trees and boulders in them. You might have a few, but it's mostly just mud. Okay, so this is caused by long, prolonged amounts of rainfall, and it has a lot of water in it. As a matter of fact, it has more water than an earth flow. Okay, so mud flow, more water content than earth flow and can move quickly. So these things can move very, very quickly, almost like a river. Okay, these can act just like a river, like you saw in the debris flow. It's just like a lot of mud. Okay, does that make sense to everybody? Okay, not hearing anything. Then you've got an earth flow, which will move slower. Now that's one of the big things to remember. This will move slower than the mud, and there's less water in it. So go down here to these images. You can see these are earth flows. They still move quick, but it doesn't look like a river of mud. It looks like a big just chunk of mud or of earth flowing that kind of flow down the side of the mountain. That's the best way to describe them. As a matter of fact, I'm going to show you guys an earth flow real quick. Earth flow, Mongolia. This is a great image of an earth flow. You can see it's not moving nearly as fast as the debris flow. However, they can move faster. This, and you can see it's still moving fairly quickly. Now he's going to pan to the right in a minute, and you'll see that this is actually quite a bit longer. You can see it's going all the way up the hill, and it's just like this big chunk of earth that is literally flowing down the side of the slope. Okay, that's kind of how you can distinguish an earth flow. Okay, this right here is the one that happened in La Conchita. California, very, very sad, wiped out a bunch of houses, killed entire families. So these are commonly on slopes from 10 degrees to as steep as 30 degrees. So you can actually be a really, actually not very steep slope, as you saw on this one in Mongolia. But the key is right here, initiated by periods of prolonged rainfall. And sometimes don't initiate until well after the stormy or rainy season has passed. And that's just because the water gets in there, it saturates the ground. It can take a long time for it to move, and then it'll slowly move. Okay. And then you got creep, which is just it freezes, and as the ground freezes, it expands, moves forward a little bit, thaws, goes straight down. Freezes again later that night, expands a little, and then in the morning it thaws and goes down. And it has a slow forward motion, just inch by inch by inch. It's very, very slow. So yeah, we'll go here. I was talking about the trees. You can see they have a bit of a bend to them. That's just because it's been moving. The trees have been kind of pushed to tilt sideways, and the tree slowly, as it grows, corrects itself to go straight up. All right. We're not going to talk about cliff retreat. That's just where it falls. So water waves are coming in. They can undercut underneath the base of the mount or under the base of the cliff. It can fall just as it's weakened from that and exposes the terraces. And we'll move on from this. So that one, I wanted to spend a little more time just going over each type of landslide. Landslides happen. Okay. And we'll briefly go over landslide mitigation. So there's some things you can do for landslide mitigation, right? Slope reduction. So make it, if you've got a steep slope, make it less steep by terracing it, or literally going up with bulldozers and taking off stuff up the top until it's more gentle. You can do other things where you add more stuff to the base. So that's a great way. Surface and subsurface drainage. So that means you can just make sure that water doesn't get trapped in the soil, that you have routes for it to go out so that it doesn't get in the soil and weaken the surface. Terracing, rock walls. You can plant plants with deep roots, or you can do what's called buttressing. That's just where you put a heavy layer of big rocks to blanket the slopes. We'll show you some examples here. So here's terracing. You've got this slope right here, prone to a landslide. They've come through, cleaned it up, put terraces in, put retaining walls. This significantly strengthens it. This slope, you can see it's really sloped here, and they came through and put a whole bunch of big rocks on. That's the buttressing they were talking about. They probably also lowered the angle of the slope as well. They dug it back so it's not quite as steep, and they put the heavy rocks on. Right here, they just came through, planted vegetation that sinks down deep roots, and it really stabilizes, acts like rebar to catch it and keep it in place. And this is buttressing, and what they've done here is they've literally sprayed concrete all on this and kind of put a big cast on the outside to kind of hold it into place. That's another example of that buttressing. So these are all big things to do. Keep in mind, another thing to keep in mind is that homeowners insurance typically does not cover landslides. They often have a caveat in homeowners insurance saying that they will not cover what are called acts of God. And that's these just big random things that can be hard to predict, like landslides, tornadoes, things of that nature. Okay, and warning signs, remember, if you guys remember I saw many of you in your great dates for this week. Well, not this week, but the landslide week. You guys went around, walked around your neighborhoods, and you looked for things like cracks in the sidewalk, or bulges in the ground, leaning telephone poles or trees, sunken or dropped down road beds, things like that. So these are all signs that you can see in your community of potential for landslides. You can also look for seeps, where just water's kind of seeping out of the ground. or just like really like the creek levels or the river levels rapidly rising, things of that nature can also be signs that a landslide is prone to happening. This is another one. If you see soil moving away from your home, that's a bad sign. Decks, patios, things like that starting to tilt over. That can be a sign of landslides as well. It can also just, if it's over a long period of time, it can just be settling from your home. But if you see it within a year, all of a sudden really start to tilt, that could be a sign you might have a landslide coming. Offset fence lines or cracking in your concrete floors and foundation. All of those are signs that you may be in an area that is experiencing creep at least, or may be prone to a landslide in the future. Okay. I would come back, go through this slide in particular, what a homeowner can do to mitigate landslides. These are not only just good for life, you know, teaching you what you can do to protect yourselves, but there will be some things there might be some things on the test, like what are some things you can do to protect your home or mitigate against landslides. So you could put, you know, and they'll have options like avoid removing material from the base of a slope, and then a couple other options. So make sure you know some of these points, come back through and go through them. And then during a landslide, what to do: stay alert, awake. A lot of times people get caught in them while they're sleeping. So stay awake, listen to the radio, consider just getting out of there. A lot of times that's the best thing you can do. Just get out of the region if they say there's a landslide occurring. And listen for those creaks and groans and weird sounds. And stay away from rivers, valleys, you know, gullies. That's where a lot of the stuff is naturally going to want to come down. So yeah, don't stay away from bridges. Beware of aftershocks. And more, if it's an earthquake that's causing it, be aware that an aftershock can trigger another landslide. If you think a landslide is going to happen, just get out of there and evacuate. So I think that's all we're going to talk about with landslides. Is there any questions on landslides? That should give you a good overview for what you need for this. As a matter of fact, let's look at this right here. Come on, go back up. So I think we went over these things. No, how to stabilize slopes, prevent and reduce mass wasting. We just went over that. Different types of mass wasting. We spent quite a bit of time on that. That's a duplicate, the next bullet point. What contributes or triggers mass wasting, angle of repose, and areas that are susceptible to landslides. So no general, but some specific. So you should know that areas in the Rockies or in California or in the Appalachian Mountains are prone to that. Okay? So great. There's that. Any questions on anything we went over, anything that you see right here on this review? By the way, this was posted in the announcements. So this is I think it was in Monday's announcement that this was posted. Maybe it was a little later, but this is up too, with the videos for you guys to watch. Okay, we gotta here. Yes, so I'm gonna be posting those literally right after this. Okay. And as a matter of fact, I'm going to post them, but I'm also probably going to send them out to you guys all in an email. So you'll be getting one more email from me tonight. Sorry, you guys have gotten a couple, but you'll be getting one more. You'll have those. You can just look through them, make sure you know it. I might actually extend the test deadline until Monday, unless anybody opposes. I can keep it tonight to Saturday, but I don't think anybody will oppose that. But yes, the case studies ones will be posted tonight. Okay. All right. Then what we're going to do with flooding, oh, got another. You got it. We'll do Monday. Okay. Okay, so now I'm just going to get the chat open over here. Okay, perfect. Flooding, these are some things to know. Factors that increase flooding and flood risk. The effects of dams, levees, urbanization, and other modifications. Braided versus meandering streams. 100 years floods. What does it really mean and how is it determined? Velocity and discharge of rivers, what influences it? Where do rivers flow the fastest? How is it measured? Flood insurance and landforms that form around rivers, so floodplains, alluvial fans, things of that nature. So what I'm going to do is go back through, go through some of the presentations again with this for you guys. And we're going to talk about them. And then we'll come back and see if there's any questions. But to start off with, let's see, this is landslides. I'm going to close out landslides in the calendar, guys. Okay, now, river systems, perfect. Are there any initial questions on floods, rivers, anything like that? I'm not hearing anything yet. If at any point during this you have a question, just pop it up in the chat. Just unmute yourself and say, "Hey, Brother Northrop, we've got a question. You need to stop talking and listen for a second." So, without further ado, we'll talk about first river systems. That's where I want to start. This is my favorite thing. That's what I'm doing. I'm doing my PhD on river systems right now. I could talk your ear off about these, which I'm not going to do. You guys have other things you want to do. But start off with, there's two types of rivers that we talk about, right? There's meandering rivers right here. And down further, we've got braided rivers. And when you look at these pictures, they look very different. And that's because of a few different reasons. So this braided river, you can see there's a main trunk, but then you've got all these other trunks coming off of it. And it looks like there's this big tangled mess of channels and everything. And they're really cool looking, really beautiful. They leave a lot of cool sediments and make really cool rocks. But they're really, really different looking than if we just go up here to our meandering rivers, where it's one big channel. I'm going to look at this one right here. One big channel going through and sinuous and curving, almost looks like a snake. So they're two very different looking systems. And they have some important differences that we need to point out. So first, at this one. Meandering rivers, this is when a river travels across a really flat land, really flat surface, and it literally just kind of moseys. It meanders back and forth and gets this beautiful sinuous shape, curvature to it. And it's just as it moves slowly back and forth across the floodplain. And there's a reason for that, okay? There's a reason that it gets curvy and it doesn't just stay straight or anything. And I'll show you with this picture right here. Now, with rivers, there's two things happening in a meandering river simultaneously. You have deposition and you have erosion. So what's deposition? Can anyone talk about what's deposition? Does anybody know? Okay, we got a chat here. That's right. It's depositing. Great, Karen. So it's depositing on the inside bend. And so what that means is it's taking and dropping sediments and sand and dirt and silt and clay and depositing it in a layer on the ground. So it's actually building new ground right here. And just like you said, Karen, on the inside of these bends, on these what are called point bars. Okay, so it's depositing in here sand. Now, where's the erosion happening? And what is erosion? Anybody? That's right. Very good. It's the wearing away and the making the river wider. So what's going on here is we're getting on these outside banks, this cut bank, that's where the river's moving the fastest around those outside edges. And it's actually scraping up the dirt and the sand there and picking it up and carrying it off. So what's happening is you're getting deposition right here where it's building out sand. And at the same time, it's cutting away sand out here. So it's not widening the river so much as it's building it out more into an even more curvy shape. It's accentuating that bend. And it's going to get worse and worse and worse. So that if we go up here, this shows the evolution of the Mississippi River. And all these different bends are different bends that have happened over time with the river. And eventually what happens is these bends can get so big that finally the river is just going to say, you know what, I don't want to travel all the way over here. So it just cuts through and makes itself a little straighter. And that's what happened right here. The river used to go all the way out here, but then it started eroding in this inner bend, and it got so close to erosion over here, it just naturally created its own stream, and it completely cut out this bend. It seems kind of weird. It's kind of hard to wrap your mind on sometimes, but literally they can they're always changing shape, and they're keeping these bends, and they're building new bends and depositing and creating these, point bars, these little sandy beaches on the rivers. Any questions on that? Feel free. If you have a question, please let me know. I can help you understand, hopefully. Okay. Now let's talk about, in a meandering river, the locations of things. So, or kind of the location is not the right word, but the construction, the different parts of a meandering river. So right here, you've got what's called the channel, right? That's basically just where the river is normally. That's the river itself. That's just where at low flow stages where you're not flooding, the extent of the river. Then you've got what's called the hydrologic floodplain right here, okay? This is up a little bit. You've got these little banks, little higher elevation. This is where when you have seasonal high water, so in the spring when you have all the spring runoff, this is where the river fills to. Typically you won't have trees in here. This is just kind of that high water mark. Okay, and then you've got what's called the topographic floodplain. Okay, and that's this outer area here. It's where you're going to have your levees or your bluffs or whatever. And this is where the river will only fill up to here when you're flooding. Most of the time, this is just kind of this flat surface on the sides of the river. It's got trees, it's got grass. Sometimes cities are built in here. And this is the area that will flood when you get like a 100-year flood. So if we go down to this picture, we can see those different parts. So right here, you've got your channel, and you've got what's called the leveed floodplain. So this is where they've got the levees, kind of those walls that build up to contain a river. This might be the leveed floodplain, might be when, you've got the spring runoff. If you have a really bad spring, it might fill up to here. Then you've got bluffs out here, and this is your topographic floodplain, right? So you've got these natural bluffs that contain it. If you have a really bad year, the river will probably, like a really, really bad year, it'll flood up to these bluffs, and this whole area will be a big channel. And sometimes if it's really, really, really bad, it can even extend out further. But this kind of gives you an idea. You've got your topographic floodplain, your levee floodplain, which is like your hydrologic channel or a floodplain, and then you've got your channel here, okay? And we'll talk a little more about levees and things like that. Let's see, anything. Good question. The question is, are levees man-made or natural? And the answer is both. I know that doesn't necessarily help, but they are both. I'm going to actually skip graded rivers for a minute. We're going to talk about levees, and they are on the next PowerPoint. Overview, flood monitoring, I might have accidentally closed the one I want. Yep, I did. So I'm going to open up. Okay. So in many instances, you can look at something like this, where the levees are man-made. So I think this is in California, but they've basically built up this big wall, and it contains the river so that when it floods, it's going to hold up the river up to this height. Okay, so this is a levee that's an example of a levee that's man-made. Now, if we go up, we can look up natural levee. You'll get what are called natural levees. And this are these berms right here. And basically what happens, and you don't need to know how levees are made naturally in great detail, but essentially what happens is the river is going to start flooding, and as it flows over the banks, the water is going to flow slower as it's flowing over the banks. And what happens is as the water flows slower, it's not going to have as much energy or strength to carry the bigger particles of dirt and sand and clay. And so that's going to actually deposit. Okay, and it's going to create these banks of mud, and it's going to build them up after every flood. So it's going to build these levees up naturally as it doesn't have the power to carry carry the river or carry the mud. And so it's going to build these natural banks up the side. And I'm going to see if I can find a diagram here. It's not going to have as much, it's going to build these up, and you're going to have these little berms over that. It's going to naturally increase the size or the height of, and those will be natural levees. Okay? Does that make sense to everybody? Clear as mud, right? Okay, great. All right, we'll go back to this one. Okay, back up to here, braided rivers. We've also got braided rivers. So this is when the river is choked with more sediment than can carry. So what that means is there is a lot of sediment and silt and sand and stuff in the river. And what it means is it deposits a lot of sand, a lot of sediment. It can't get very deep. They're not super deep. And often it's a very rocky area, but you can see this whole area. When this floods, all of this will be covered in water. And basically, when it floods, all of this sand and gravel you see right here is going to be stripped away and taken downstream. So there's that. Other thing is the water in these streams is faster moving than what you would see up in the meandering systems. So this is faster moving water as well. Okay, and you can see here, this is right here, this is 7 to 10 miles wide. So when that floods, that's going to be 7 to 10 miles wide of water. Okay? Any questions there? Okay. Here's showing your topographic floodplain. You got some bluffs over here and over here. Here's the leveed floodplain. This is where the levees are and all the braids are. You can see here's all the channels. When it floods just smaller levels just within the levees, this is going to be solid water. If it breaks through the levees, it's going to go out to here and out to here. This is the Snake River near Jackson, Wyoming. Okay. Then you've got what are called mountain streams. These are extremely fast flowing, steep gradient. This is like the Thompson Falls case study flood that you guys read, or Big Thompson Canyon, excuse me. So these are very high gradient. These are the roaring rapids that people like to go whitewater rafting down. You know, very high energy. Okay. You've got drainage basins. We'll talk about this really quickly. A drainage basin, this is just the entire area or that is going to drain into one main trunk or main river. So for example, this is the Mississippi River Drainage Basin. And what this means, this outline here, is all the rivers within this area go into the Mississippi River and go out of New Orleans. Okay, so everything up in Montana, parts of Canada, all the way over to Colorado, Wyoming, you know, parts of New Mexico, all the way over here into Pennsylvania, New York, areas of that. All of this water is going to drain from all these mountains and areas over here into the Mississippi River down in here. And that has a really important implication to flooding. Okay, and that is that right here, you can get heavy snowfall in Montana that can cause flooding in Nebraska. Because this can melt, and all this water in Montana, Wyoming, Colorado can then get into Nebraska, fill up these channels, and flood. Okay? So there's erosion. Your floods can come through, erode out the sides of the bars, and break down houses into the water. I don't want to talk too much about that. I think that makes sense. Let's see here. Overview, flood monitoring impact. So it can be caused, flooding can be caused by snow melt, flash flooding. I don't want to spend too much time on these things. Okay, mud flows, fans. Okay, last thing I want to spend some time on with flooding, I'm gonna go back to this here, is, oh, I do want to open that other one. Sorry guys, I just want to open one last slides, floods.
I actually have a quick question.
Yeah, go for it.
Yeah, I was just wondering, I just thought it was worth it, but the topographic floodplain you're talking about, is it possible when the river floods that it can go past that point, or is that like the point where the flood stops?
It can. I mean, it's very rarely, but for example, when you get these like, so you guys remember, right? You've got your 100-year floods, which are really, really big floods, right? That statistically, you know, you have a 1% chance of it happening every year. So these are really, really big floods. Well, there's something actually called 500-year floods, and they're just these big, big, big floods. This is stuff like what I'm talking about with, like, you know, the China 1931 flood, right? And this is the one that like devastated China. You can get these big floods that will break over them, but they're not very, very common. Typically, it won't break through it, but you know, they happen. You know, you can have them in Nebraska. I think the one that we just had just this last year might have actually broken the topographic floodplain in some cases. Yeah.
Okay. Yeah, I was just wondering if that.
Yeah, you can have that. Absolutely.
Thanks.
All right. And that's a great question. Okay, we're gonna hit a few quick things on this. One real quick, and then we'll wrap it up. Oh, you know what? Where is it? I want to talk about discharge, but for whatever reason, that wasn't the right one. All right. Sorry, I accidentally closed the other presentation that I wanted. Okay, it's the third one that got closed. All right. So this one's going to last few things. So measuring floods and things of that nature. So the first thing is what is discharge? Discharge is where we look at the area of the river. So how much area, cross-sectional area, so basically the channel, at times the velocity. So how fast it's moving. That's all discharge is. So make sure you know that. So you know it's basically depth of the water by the width. So depth times width times velocity is your discharge. Okay. So we'll leave that along with that. This is a really good graph. You should look at this. And what this is showing, and this is time, and this is your discharge. So you get rainfall right here, a bunch of rainfall. Then you have a bit of lag time. This time where it's still coming down the mountain. And then a little while later, all of a sudden you'll get all this water flooding the rivers, because it takes a little bit of time between when the rain hits for the flooding to actually start to happen. Oftentimes, not always, but rainfall in the mountains can cause flooding a few days later down in the valleys. Okay, so that's a good thing to know. Now this one is what I wanted to spend a few seconds on. And I don't necessarily want to read this, but it's really important to know what a 100-year flood is. And you guys did really good on your guided labs explaining this. But a 100-year flood is simply a statistic. It's not that meaningful. Really what it is they look back at the last 100 years, they find the biggest flood and say, okay, there's a 1% chance that a flood that big will happen every year, or happen this year. So it's just a simple statistic. It's not based on any solid science. So that's a good thing to remember. So a good question that you might see pop up on this test is something along the lines of, your coworker says that they had a big flood 100-year flood last year, so they're good for the next 100 years. You know, is this true or false? If it were true or false, or explain why, why this is incorrect thinking, and then they would have a multiple choice with a couple of options trying to explain it. And the one you would want to use is the one that talks about how it's a statistic, and it simply means that there's a 1% chance of a flood that size happening that year. Okay, so know that. Flood mitigation, some things. So dams can help mitigate against floods, where we can control the runoff. So if we have a really wet year, we can decide to retain a little bit of the water and control the amount of water coming out of the reservoirs down to the rivers, down into the cities, so that it's not just all flashing down at one time. You can kind of trickle the flow a little bit. Levees can help, right? They can help contain it. But there is one problem with levees. Levees can break, like this. If a levee breaks, all of a sudden, all that water is going to come rushing in, and it's going to be a little bit bigger of a shock than if you had a little more gentle rising of the water. But the reality is, either way, the flooding is still going to be really bad if the levee breaks, or you never had a levee in the first place. Okay. So this is just showing different ways a levee can break. You can get overtopping like this, which is just literally more water than the levee can hold. It's like overfilling your cup of water. Okay. You can get where the levees are permeable, which just means water can travel through the levee. Waves can come through and break the levee down. Another thing that you can have happen sometimes is a pipe break, or they find water can start transporting under the levee. That'd be like your sewer system somehow starts malfunctioning, and it gets through the sewers and starts going under that way. You can get the levee breaking and failing just from erosion. So these are all different ways levees can fail. So you've got channel modification as well. That just means, removing brush and trees, deepening the channel and widening it. Things like that can kind of help. Rip wrap, and what that is basically you cover the sides of the channels with big boulders that are hard to move. And that's kind of like the buttressing that we talked about with landslides. And you're just putting up these hard walls that will protect that the river, for the most part, won't be able to move away and erode away. So that'll protect against erosion. Okay. One of the things to know too is the role of urbanization and flooding. A lot of times we like to put concrete down, and water can't get through concrete. So a lot of times when we have a lot of rain, we can cause urban flooding, where the water overfills the sewer systems, the drainage systems we have, and then it'll just be running like torrents and rivers down the road, and we can cause flooding that way. Sedimentation can cause flooding. So basically, if you get a lot of sediment into your water, it can actually carry, like once the water retreats, it can actually leave like even sometimes a few feet of dirt and clay and stuff along the ground where the flood took place. You can actually cake whole towns in a couple of feet of mud. Happens oftentimes. We see this after hurricanes, after the storm surge comes in places like, with Hurricane Harvey just a few years ago in Texas. Okay, I'm not going to talk too much about this or this. So I think that sums up everything I want to talk about with flooding. Is there any questions you guys have on this? Okay, I know it's kind of later, ran over a little bit. That's fine. If you have any more questions, email me, or hold out Tuesday or Monday. I'll probably do that review for you guys as well. I'll post that. Yeah, it'll be Monday because I want you guys to have enough time. So for Saturday. So I'm gonna post send those 2 documents out in an email to you guys. I'll probably get these videos, since they're about an hour long, take a little longer to post. So it probably won't post until, I'll try and get it posted tonight, but it might not show up till tomorrow early in the morning or tonight late at night. So I'm going to extend the test until Monday night. And you guys will get that email here in about 5-10 minutes, okay? All right. If there's no other questions, go through these case studies here on this. Gotta chat real quick. Yeah, of course, Marilu. So on this document, all these questions on these case studies, the documents I'm sending you guys has the answers to them. Okay, so it'll have the answers to all of these things. Okay? All right, guys, have a good night. If you have questions, email me, contact me. Always feel free to do the extra credit. If you want more, just shoot me an email. I'm going to work on getting these things added in tomorrow, the extra credit. So you should start seeing test grades go up. And don't worry, if you guys are feeling worried or stressed about your grades, if you're doing your homework and you're trying on the tests, you're going to pass the class. I'm not a believer in, I'm a firm believer that if you put in the effort, even if you're struggling, you're going to pass, okay? So don't worry, guys. Like, I'm going to adjust the grades. I'm going to put in the extra credit. The final, particularly, I usually adjust. So don't worry. Going to make sure you guys pass, okay? All right. Well, you guys have a good night. I'll stick on for a few minutes in case anybody has any questions they want to ask. But yeah, good. We'll see you guys Monday.
Hold on, I just saw something.
Yeah.
So I just saw in that review it said flood insurance. Was there anything you know on that? Did we talk about?
Yeah, that's a good point. Let's pull that up.
I just saw it. Sorry.
No, you're totally fine. Kind of a big point with that. And I always hate talking about. I don't mind talking about the flood insurance, but I hate it just because it's a pain to find on the PowerPoint because they don't do a good job of really going over this. But landscape sanitation. Okay. Okay, here we go. So it's on the 100-year flood stuff that they talk about it. Let me see here how they exactly say it. The biggest thing to understand is that a 100-year flood is basically solely used for insurance purposes. And it's just, like I said, a statistical projection that they're going to use. Let's see, go down here. I guess the biggest thing also with insurance is a lot of times insurance doesn't cover flooding. Or like they won't cover you if you live within the floodplain. That's a big thing to note, actually, because a lot of times if you live in a floodplain, a lot of types of insurance don't really want to cover you, or if they do, it's going to be a higher premium.
Yeah, because it could happen.
Yeah, it's a high risk area to live in. Does that kind of make sense?
So yeah, so you said that the 100-year flood statistic is the insurance.
It's not that it's in insurance, but that's that's a metric they use to kind of forecast it. It's just a way they try and keep, I don't know, it's the way they kind of use it to try and determine their risk, if that makes sense, right? Because insurance is all about risks.
Yeah.
And so that's how they gauge their risk. Because if you live in the 100-year floodplain, if you live in a 50-year floodplain, or they've got it all graded out that way.
Okay.
So
if you live in that little 100-year,
yeah, you're gonna
probably won't get insurance.
Won't get it, or it's gonna be harder to get.
Hard.
And the other thing is they'll have limitations on coverage of what they'll give you, like what they'll restore to you. So, and I don't know what that is. I think that varies from insurance to insurance. So, good question though.
Yeah.
Anything else, Caleb?
Trying to think. Where's that one below the?
Say that again.
I was just looking at so the landforms. You're just running the flood insurance landforms that form around rivers.
Okay, that was just, you remember me talking on the meandering rivers, and I said there's the point bar.
Oh yeah.
That's one landform, and then there's where the erosion's happening called the cut bank. So there's that, and then there's like the floodplain, things like that.
Okay. I don't think. Oh wait, I did. So the braided rivers. So pretty much like all we need to know for those is that it's kind of like the sediments. You said it. So it like kind of chokes up the river, so it like stops the flow, so the water tries to find a new path, and that's what makes all the like.
Yeah, it's not like necessarily that it's getting a new path. It's more that it's getting a new path. It's not that it's like stopping the flow.
Excess water.
Yeah, it's like it's shallowing the river, and so all of a sudden it's branching out, and it's branching out into a whole bunch of other rivulets and streams, kind of widening itself that way. Because it's actually flowing faster than a meandering river would.
Okay, that's the point.
Yeah.
Okay.
Cool. Great question.
Sorry, I just kind of thought these like
No, usually a lot of times for me when I sit in reviews and stuff like that, I don't have the questions until afterwards. So.
Yeah. Okay. Good.
Any other questions? Anything?
And then, so all we need to know for angle repost is that it's just the angle that can cause a risk of a landslide.
Yeah, and do you remember the angle?
It was 35 degrees.
Yeah. Yep.
I think that's about it.
Okay.
I think that's all.
Cool. Yeah.
Well, thanks for the view. That was good.
And if you think of any other questions, like just shoot me an email. And if you think of more even after the test, bring them Monday. I love to answer them on then, or watch the video. The other thing too is I've got another review posted in the announcements. It was actually just last semester's. Watch that one too. Go over a lot of stuff. Have a little other PowerPoint. I did it a little different way, format than this one. So there should be plenty of material to go over if you have questions too before. Okay. All right.
Okay, sounds good. And then you said, I might have missed it or misheard it, but you said this test was moved to Monday, or what did you say was moved to Monday?
I'm gonna adjust the due date of this exam to Monday night.
Oh, okay.
So you have weekend. You have all of Saturday, Sunday, and Monday.
Okay, cool.
It's hard. You're right. The 7-week. This is my first time ever teaching the 7-week break.
Yeah.
And it's really hard because it's so compressed for you guys.
Yeah, I was kind of afraid. It was my first time doing the 7, but it actually hasn't been as bad as I thought.
Well, good. I'm glad. I I'm not a fan just because I feel like I like to take time. You know, normally I like to do videos every week, but
Yeah.
between trying to get your guys' grading done and you guys trying not to overload you guys with things to do, it's just hard. Anyway, have questions, let me know. Okay.
Yeah. Right. I'll email if you have any.
Perfect.